Hello everyone, I'm going to introduce you all to my topic Apache Spark. So let's begin with the introduction of Apache Spark. Apache Spark is an open source cluster computing technology designed for fast computation. It was originally created at the University of California known as the AMP lab and is now shifted to Databricks. Apache Spark is based on Apache Hadoop MapReduce and extends the MapReduce model to efficiently use it for more types of computations, which includes interactive queries and stream processing. The main feature of Spark is its in-memory cluster computing that increases the processing speed of an application. Apache Spark uses Hadoop in two ways, that is for storage and computation. Since Apache Spark has its own cluster management computation, it uses Hadoop for only storage purpose. Now let us see some of the main features of Spark. The first distinguishing feature of Spark is its speed. Spark helps to run an application in Hadoop cluster up to 100 times faster in memory and 10 times faster when running on disk. This is possible by reducing number of read-write operations to disk. It also stores the intermediate processing data in memory. Another important feature of Spark is it supports multiple languages. Therefore, you can write applications in different languages. Spark comes up with 80 high-level operators for interactive querying. Another feature of Spark is advanced analytics. Spark not only supports map and reduce, it also supports SQL queries, streaming data, machine learning, and graph algorithm. Now let us look at the components of Spark. The first component of Spark is Apache Spark Core. It is the underlying general execution engine for Spark platform that all other functionality is built upon. It provides the in-memory computing and referencing data sets in external storage system. Another component of Spark is the SQL Spark. It is the component on top of Spark Core that introduces a new data abstraction called Schema RDD, which provides support for structured and semi-structured data. Spark Streaming is another important component that leverages the Spark Core's fast scheduling capability to perform streaming analytics. It ingests data in many batches and performs resilient distributed datasets transformation on those mini batches of data. We'll see the RDDs in the upcoming PPT. The next component is Machine Learning Library. It is the distributed machine learning framework above Spark because of the distributed memory-based Spark architecture. It is 9 times as fast as Hadoop disk-based version of Apache Mahout. GraphX is the important component of Apache Spark, which is the distributed processing framework on top of Spark. It provides an API for expressing graph computation that can model the user-defined graphs by using an abstraction API. So now let's see the actual working of Spark. Spark has a small code base and the system is divided in various layers as you can see in the diagram. Each layer has some responsibilities. The layers are independent of each other. The first layer is the interpreter. Spark uses a Scala interpreter with some modifications. As you enter your code in Spark console, Spark creates an operator graph. When the user runs an action, the graph is submitted to a DAG scheduler. The DAG scheduler then operates the graph and divides it into a number of stages. A stage is comprised of tasks based on partitions of input data. The DAG scheduler pipelines the operators together to optimize the graph. For example, many map operators can be scheduled in a single stage. The final result of DAG scheduler is a set of stages. These stages are passed on to the task scheduler. The task scheduler then launches these tasks via task manager. The worker then executes these tasks. A new JVM is started per job. The worker only knows about the code that it is passed to. Now you must be wondering why actually we have to use Spark. So to get an answer to this, we first have to learn about the most fundamental component of Spark, that is the resilient distributed datasets. It is the fundamental structure of Spark. It is an immutable distributed collection of objects. which means each data set in RDD is divided into local partitions which can be computed on different nodes of the cluster. RDDs can contain any type of Python, Java or Scala object including user-defined classes. Formally, an RDD is a read-only partition collection of records. It can be created through deterministic operations on either data on stable storage or another RDDs. Basically, RDD is a fault-tolerant collection of elements that can be operated in parallel. Now, there are two ways to create RDD. First way is by parallelizing an existing collection in your driver program, or the other way is referencing a data set in an external storage system such as HDFS, HBase, or any other data source offering a Hadoop input format. Spark makes use of the concept of RDD to achieve faster and efficient MapReduce operations. Let us first discuss how MapReduce operations take place and why they are not so efficient. So we all know that MapReduce is widely adopted for processing and generating large data sets with a parallel distributed algorithm on a cluster. It allows users to write parallel computations using a set of high-level operators without having to worry about work distribution and fault tolerance. Unfortunately, in most current frameworks, the only way to reuse data between computation is to write an external stable storage system. Both interactive and iterative applications require faster data sharing across multiple jobs. Data sharing is slow in MapReduce due to replication, serialization, and disk input-output. So as you can see in the first figure, the iterative operations on MapReduce are illustrated. In these, while doing these interactive operations on MapReduce, there are substantial overheads due to data replication, disk I/O, and serialization, which makes the system slow. Another figure demonstrates the interactive operations on MapReduce. So during these operations, the user runs ad hoc queries on the same subset of data, and each query will do the disk I/O on the stable storage, which again dominates the application execution time, and the system begins to run slow. Now let us see the data sharing in Spark and why it is more efficient than MapReduce. So we all know that data sharing in MapReduce is slow due to replication, serialization, and I/O. They spend more than 90% of the time doing HDFS read-write operations. So recognizing this problem, researchers have developed Apache Spark. The key idea of Spark is RDD, which we have already seen, and it supports in-memory computation, which means that it stores the state of memory as an object across jobs, and the object is shareable between those jobs. So this makes the processing 10 times faster between the disk and network. So as you can see in the pictures, the first picture demonstrates the interactive operation on Apache Spark. So here the intermediate results are stored in a distributed memory instead of disk storage, and hence the system becomes faster. The next figure illustrates interactive operations on Spark. So here different queries are run on the same set of data, and this particular data can be kept in memory for better execution times. Let us move on to the applications of Spark. So Spark, as we have discussed already, that Spark is used for stream processing, machine learning, interactive analysis, as well as data integration. As Spark has the modular nature of API, it makes it easy for engineers to factor work into reusable libraries and test it locally. Spark's users choose to use it for their data processing application because it provides a wide variety of functionality. It is easy to learn and use and is mature and reliable. Thank you.